Hello, I'm Tim Holy from Washington University in St. Louis.
And I'm Valentin Churavy from the Julia Lab at MIT.
And today we're going to be talking on the topic of package precompilation. This is collaborative work between the two of us that's really aims at trying to make the overall Julia ecosystem more pleasant to use and more effective for a wide range of people. So one of the things that we all love about Julia is that Julia code runs fast. This is the so-called micro benchmarks figure that many of you might have seen before. And what you can see is that Julia's execution is comparable to the execution of the fastest languages that we have. Julia can even be written to write some truly heroically fast code. For example, can produce results on matrix multiplication that are equivalent to the fastest libraries known. So Julia is second to none in terms of its overall runtime performance, and we love that about Julia. Another thing that we love about Julia is the fact that you can write fast code quickly. And this shows you an example that I've encountered in my own work. In this application, we have a series of image volumes over time. The raw files on disk are a terabyte or larger often. But if we want to visualize them interactively, sometimes we want to visualize this three-dimensional volume, and we might be interested in just a single slice plane through that 3D volume. But that slice plane might be at an arbitrary tilt angle and with respect to the axes of the acquisition. So since the array data are too big to load into memory at once, you might want to do this in a lazy fashion. And if you were doing this in Python, you would use this amazing library called Dask to sequentially, lazily load the large file and then retrieve just the data that you need to do the computation. If you're using Dask, the developers recommend that you tune the so-called chunk size for optimal performance in your application. And if you do that, I found on my machine that I can get about one of these slice planes in about 1/10 of a second or so. The Julia code that's corresponds most directly to the Python code is this dot here. And this dot here, you can see the execution time is about 1/40th or so of the fastest possible option on Python. So as we've seen over and over again, Julia substantially outperforms Python, and even under more demanding circumstances where the data aren't yet even available in RAM and where you're using only one thread instead of 6, Julia outperforms Python by a large margin. But the most impressive thing about this is the amount of code you have to write to achieve this. And Python, while using Dask is quite straightforward, they've made it easy to use. The reality is that the underlying library is about 12,000 lines of Python code if you exclude comments and blank lines and other things like that. Whereas in Julia, you can write this in just 18 lines of code just using base Julia and the standard library. So not only can you write fast code, but you can write fast code that outperforms Python within very few lines of code. However, Julia does have a major usability problem, and this is often called its latency or the time to first plot, or the term that we'll be using most often in this talk, time to first execution. And we actually want to do a little demo of this, just so you see for yourself what this is really like. So I'm going to copy this command here. I'm going to be using, not to pick on this amazing plotting library called Maki, but and I'm using, actually, let me use Julia 1.7. And so I'm going to be using Maki. So first of all, I'm going to load the Maki package, and you can see here it's thinking for a little bit because it does take a little while to load all this code into your session. And then we're going to plot something. And here I've launched the plot, and you can see there's no plot up on the screen. Well, while we wait for that to come up, let's try Python. Okay, so here, if we go back here and we look at the Python equivalent of this, this is using matplotlib. I'm going to copy this, and I'm going to switch back to Julia, to my console here, and we'll launch Python. And if we copy all this, boom, here's the Python figure. How's the Julia code doing? We're still waiting for the code. So let's see, something should happen at some point and see if is there a window up? No window yet. But let's wait and see. So yep. So here you can see the window is starting to appear, but we still don't have any data. in the window. So what's going on here, in the first step, we waited for Julia to load the code. And then the second one, the code is in the session, but it hasn't been compiled for the specific types that we're sending to the screen. And so all of this time that we spent waiting here was for Julia to compile the code. And once it's compiled, now you can see the plot. If we try to get a second plot, you can see, boom, it pops up right away. So that's lovely. So once you've compiled the code, Julia is incredibly fast and responsive and a real pleasure to use. But that initial usage is quite painful indeed. Okay, so let's go back to the talk here. And this is called that time to first execution problem. And it, as you just saw, it actually has two halves. The first half is loading the packages in the first case. And we're only going to touch on that briefly today. And that's not something that we're actively working on. We want to get to that eventually, but that's really not the current focus of our work. Because as you saw, it's actually that the compilation process takes much longer than the loading in a large majority of cases. And this is the thing that Valentin and I are working on trying to reduce a great deal. So there are a number of strategies that you could use to reduce this wait for compilation. The first and truly best option would be to make the compiler faster. And there's actually been a lot of beautiful and amazing work that's been done to get us to where we are already, and ongoing work to improve it even further. So this is an absolutely terrific thing to have happen. Another option is to compile as little as needed, and there's some really beautiful work that's going on now to implement what's called compile on demand, where the last step of compilation gets deferred until we're actually executing a code. So currently we compile everything we might use, and this would only compile the parts that we do use. So that's great too. But then the third option might be to reuse the compiled code. We spent a lot of time waiting to compile that code, but we probably sent plots to Maki previously, right? It would be really nice if it could save the compiled code in a way that would allow it to be reused. And that's what precompilation is about. And so this is the main focus of today. Now, do we really need all of these steps? Could we just make the compiler faster? That would truly be the best answer. There is no doubt that that's the case. But again, just to emphasize the point, if you look at the gap between Julia and Python and loading, you can see there's more than an order of magnitude separating the two to load the package. And there's more than 2 orders of magnitude separating the time to render that very first plot compared to Python. After, again, the first time, we're as fast or faster than Python at doing this, and we can do amazing things. But it's really that first one where we suffer by comparison. And so, to my eye, I think that this 2 orders of magnitude is really what our target is. We want to make things faster by about 2 orders of magnitude. And there's been already so much nice work that's been done on optimizing the compiler that I'm skeptical that there's another 2 orders of magnitude for us, to extract. I hope to be proven wrong someday, but until then, it seems likely to me that some form of precompilation is really a necessary step for us. So we're going to talk today about what gets saved currently from Julia's compilation pipeline and what we're doing to try to extend that. So when you write source code, you're editing a text file, and that's your source code file. And the first thing that Julia does, and there's a concurrent talk going on this very topic right now that I'm looking forward to watching at a later time myself, which is about the process of turning this into so-called lowered code. This is a representation of code that is essentially a translation of your direct source code. These are stored in Julia's so-called method structure. And there's essentially one piece of lowered code for every method that you create, and this is something that gets saved to disk. And things that are saved to disk, I'm indicating here with this green color. Okay. So when Julia says it's precompiling your packages, and probably many of you have seen the animation that Julia exhibits when it's precompiling it, this is one of the things it's generating, and it's saving that to disk. Now, that's not the only thing that you can save, but to go beyond the lowered code, the package developers needed to have asked for something more. And the reason for that is because for the next step of the compilation, which involves type inference, you have to pick which types of objects you want to compile your methods for. And so the package developers might have picked some common choices that they expect many of their users will need, and they can pre-generate this so-called type-inferred code. I'm going to call these instances for the experts. These are a combination of method instances and code instances. We'll just call them instances in this talk. And these two are in green because these also can and have been for a long time stored in a precompile file, the so-called .ji cache file. Now, it's unlikely that these exist in a vacuum. So one thing that happens from this point on is so-called code generation, and this is the production by Julia and LLVM of so-called native code, the code that actually runs actively on your CPU. And this is in a red box indicating that it is not cached when you do the precompilation. So we have to generate the native code in order to run it, but we throw that away when the Julia session exits. The other thing is, since these are unlikely to exist in a vacuum, a given method instance surely calls other method instances, and we are somewhat hit and miss about what current versions of Julia can save to disk. If it's calling a method instance that's owned by a method that's in the same package that you're currently precompiling, then as long as Julia 1.0 has been out, we've also been able to store that type-inferred code to disk. But if this turns out to be an instance owned by a method that belongs to a different package, one that is a dependency of your package, then that is not saved. That just gets thrown away when that gets generated in current versions of Julia. And so what you can think of as the work of we're doing is to basically turn these red boxes into green boxes, right? And the goal then is to fill this diagram out in a manner that lets us cache everything that we might need. Okay, so what are the challenges to this? Well, one of the things that may not be obvious is that Julia sometimes discards code. And the way that this can happen is a process called invalidation. I've talked about this before, so I'll be very brief here. But basically, if you define a method and then you execute the method, it will compile it. But then if at some later point in your interactive session, you go through and you define a more specific method that would have been used by those types, then this pipeline, the answer for G of 1 should not be 1, it now should be 2. And so Julia will do the right thing and recompile your code. That means it throws away the old compiled code and has to start from scratch again. And so this process of invalidation, this is something that happens here, say, in an interactive session, but it can also happen in packages. If a package defines, say, a new subtype of integer and then creates new versions of methods for that integer, then previous code that assumed it knew about all the possible types of integers might have to be thrown away and recompilation occurs. And so invalidation used to be phenomenally common. What you can see is on Julia 1.5, which was sort of the beginning of a big transition in terms of trying to get rid of these invalidations. You can see there were packages loaded that invalidated more than 12% of all of the compiled code in the system image. And it was viewed that invalidation was so common that it wasn't obvious that it was worth pre-compiling anything because we were just going to throw most of it away anyway. But we've put some work into reducing invalidation. It's still not gone, but for many packages, it's almost negligible in terms of code that package actually relies upon to run. And so invalidation is not the threat that it once was, although it remains a problem and is probably going to be one of the last frontiers that package developers actually still have to dive into. So having largely resolved the problems from invalidation, the way is now clear to improving precompilation itself. And in Julia, I'm very pleased to report that Julia 1.8 is going to include what looks like, and in some ways is, a fairly small improvement to this diagram. But you may remember that this box used to be red, and in Julia 1.8, this box is going to be green, meaning that we have the capability now to save to a package precompile file a method instance and code instances that you specialized for types that maybe weren't around when that package was defined. And so that now can be saved to disk. And so how does that work out in practice? This shows you some benchmarks. This horizontal axis is comparing Julia 1.7, and this is the time either to load for all of the squares or to execute for all of the circles code, and it's comparing it against Julia 1.8. The dashed line is the line of equality, and so anything that is below the line represents an improvement in 1.8, and anything above the line represents a regression in 1.8. You can see in general terms that the loading for not all packages, some it's actually even faster, but for many packages, if you comprehensively precompile, they do get a little bit slower to load, but then you can see that the execution time is almost uniformly faster. And this may look like a small gain, and compared to that sort of 100-fold improvement that I think we need, it is, but it's nevertheless, I think, something you'll notice in practice. Take the example of Mach-E, for example. The time to generate that first plot went down on my machine from 51 seconds down to 29 seconds. That's a big enough change that I think you'll feel it. But the load time for the package only went up by about 1 second, right? So yes, it's worse on load time, but it's so much shorter than the benefit that you get from generating that first plot that, at least to me, this feels like a substantial win. One of the other things that you can do right now is you can modify your Julia environment for the kinds of package interactions that you need for your work. So we've long had the ability to customize your environment with the so-called Startup.jl file. And starting with Julia 1.8, I think it's going to become more useful to create a little package, which here I'm calling capital S Startup, which contains the customizations you want. And the reason for that is that the startup package, in your startup package, you can now precompile the code that you would like to have work more quickly. And if the package developers haven't, or if the package developers have already precompiled it, there's no benefit in doing so. But if you're precompiling things that aren't precompiled in the packages, then you get reduced time to first execution. And there will be soon to be released a package called SnoopPrecompile, which should make it pretty easy to make sure that all the code that this sum function needs in order to operate gets saved to your precompile files. So you won't really need to be much of an expert. In most cases, at least, you can just execute the workload, a little toy version of the workload that you want to be fast. And if you do that sort of wrapped in some of the commands that will be available in SnoopPrecompile, it should then operate in a more snappy fashion after you load the startup package. Okay, so some of you may have used a wonderful tool called Packagecompiler, and I want to compare this sort of startup strategy to Packagecompiler. So Packagecompiler wins hands down on the load time. The system images that Packagecompiler creates will be much faster to load than that Startup.jl will. Both of them starting with Julia 1.8, will save all of the type-inferred code. In Julia 1.8, we won't do anything to save the native code, whereas again, that's something that Packagecompiler is very good at. But one thing that this strategy is very good at, which Packagecompiler is not good at, is working with package updates. That is, this is just a package like any other package on your system. If you update your packages, Julia will recompile your startup.jl file as well, and you'll be able to have a continuously updating package environment. Whereas with Packagecompiler, you have to rebuild the entire system image anytime you want to update your package. So, again, there's a lot of good things about Packagecompiler, but this strategy is sort of what we're aiming to make competitive with Packagecompiler, and should have the benefit that it will work with package updates. So I'm going to transition over now to looking towards the future, towards work that is not yet done, and talk about what will be required to save native code. And I'll briefly introduce this topic and then mostly turn it over to Valentin. So as it stands currently, Julia has two independent sort of systems for storing code in precompile files. One of them is dump.c and the other staticdata.c. And they have some overlap. They can both save lowered code. They can both save type-inferred code. Only static data can save native code, and only dump.c is really usable for packages. And so one way that you can think about the work that we're doing is to try to take the best of both worlds and combine them into a single one. And at this point, I want to turn this over to Valentin, who will walk you through some of the mechanics of the work that we're doing on this.
Thank you, Tim. So one of the challenges in general with this, with being able to save and reload a native code, and in some ways we have been able to do this for a long time. So if you ever heard about the Julia system image, that essentially is us loading the entire base library and all of the standard libraries, compiling them and writing them out to disk into a single shared object file. And then on startup, we will load that shared object file, reconstitute the necessary data, and go from there. Packagecompiler takes that approach and adds the ability to add user code easily to that, and also to then create applications that you can load directly without having to go and say start Julia first. And so really, when you look at it, we have our methods. Those methods get specialized to instances, and then we write out native code. And we can save that native code. But when you're using Julia as a JIT compiler, it will play some tricks that makes it harder to exfiltrate that native code and actually load it into a different Julia session later on. One of those things is it might figure out that you're calling an external function, and it will embed the pointer at the runtime to that external function. Or for some global data that you're going to use, it will also directly embed the location of that the global data into the compiled code. So when we're doing the system image compilation, we are switching into a different mode where we're emitting slightly less efficient code, but code that we can load later. And this is in particular global variables and references to native code. And so one challenge arises is so one challenge is that we have methods being called from packages. And so if we were to think about, we want to split this large system image into many smaller package images in which we use the pre-compilation information that we have, write out the necessary things, and also save the native code, what do we need to do? And so we need to figure out whether or not we already have specialized a function, because we might be specializing a function from 2 different packages. And so, but we might never have done it in the original package. So during loading, we will need to have to resolve that conflict. And of course, when we do the loading, as we do now with our .gi files, we must make sure that actually this compiled code is still valid. You might have done some work in the REPL in the meanwhile that invalidates the native code we have compiled and cached. And so all of this capability we already had in dump.c, and we're using it for .gi files, but we're not using it for these system images or package images. And we had a lot of discussions in the community over the years about, okay, how can we get to this point of being able to cache these files? And I've been saying that in theory, compiling Julia to native code is relatively easy. We've been doing this for years, but we've been doing this in very limited circumstances. So as long as you don't need the Julia runtime, which means allocations, garbage collection, exception, multi-threading, input, output, and many more functionalities, you can cache the Julia code and load it later. Oh, and if you don't use any global data, because global data is managed in some sense by the runtime, right? An array of global data is going to be referenced through the module. So the module must exist somewhere in memory, and we must be able to reference that. And I think one of the most crucial aspects of any of these static compiling approaches that we're going to talk about in a second, is that you can't have dynamic dispatch. We must be able to see all of the code possible. And the GPU compiler approach is an infrastructure that we've written and maintained over the years that allows us to exfiltrate near static subsection codes that you might be using. And we wrote it, as the name tells us, for GPU compilation, where we already have a very restricted runtime scenario. We can't do much. We don't have garbage collection. We can only do some very limited memory allocations and so forth. So, and we can't at all do dynamic dispatch. So in that world, we can live with these restrictions, and we can cache and compile native Julia code and load it on a different device. We can even send it across the network and load it on a different machine. The next evolution of that is a project I've been working with on over the last couple of years, enzyme.jl, and it uses GPUCompiler, but it goes a step further. By loading the code within the same runtime, it can actually deal with dynamism, with runtime interactions, with all of these other things, because it is in the same runtime. And a new project that started, I think, about a year and a half ago, that's really interesting is staticdata.c, which is trying to take this approach and make it work in generality. And they've been doing a lot of great work, and they've been tackling some of the same problems. That how do we deal with global data? How do we get the compiler to emit code that is correct to be loaded at a later point? And so in some ways, what we're proposing, what we've been working on, is that we move from system images to package image. So every .gi, every cache file suddenly becomes a shared object file that contains the same metadata information for inserting methods into the method table, so that we can reconstitute the correct view into the world. It contains also a code cache for precompiled code, but we will add essentially the native code cache, where we add compiled functions. But we must make sure that this object cache is going to be relocatable. And so in order to be able to relocate code, first of all, we need to make sure who owns the data. And the global data is going to be owned, rooted in by the module in which it was declared. And so it will be serialized into the corresponding package image. If I then do a compilation depending on that data, I have to replace in the dependent compilation references to these objects with relocation entries. And then when we load a package image through Julia, we will have to reconstitute the data, reconstitute the metadata, and perform relocation during the loading process. And the PR 44527 implements this, and that's a great step forward. But right now, if you're looking very close, you might notice that functions are unnecessarily duplicated. So the sizes of these package images are too big. And so in essence, we've gotten to the point where we can have references from the red code is our package image 1, and the green box is our package image 2. And the native code that we're going to compile in package image code can reference data in the package image 1. But this native code 2 that is going to be called from the package image 2, that will actually accidentally be duplicated. And so the next step that we have to get to, and which is going to be exciting, is that during the compilation process to this to the object file, we will have to detect that we already have a version of this code compiled, and to make sure that that version is the correct version to call. And then have to replace the call with a relocation, or maybe a trampoline. We haven't fully decided on what to do there yet. Then we also will have to automate the process. Right now, if you look at the PR, it's very manual, and you have to do some work. But we can automate this process, integrate it into the precompilation pipeline, and have everybody benefit from this approach. And then, of course, once we have these files on hard disk, we will also have to automatically load them. And so one thing that we will probably not get to in the near term is, can we support the Julia feature at C callable, which exports a Julia function in a C compatible way. And so in theory, we could actually link these package images against native C applications, but that's very out in the blue. So right now we're looking at a hopeful future. In Julia 1.8, we're gonna have less invalidations, more comprehensive precompilation than in any prior Julia version. That's gonna be an immediate and noticeable win, hopefully. And then on the horizon, hopefully within the next 2 Julia versions, we will get to a state where we have much more comprehensive precompilation and caching of native code. And one of the other things that we will have to work on is when we're starting to cache more and more things, and as you have noticed, as Tim mentioned in his part of the talk, is that actually load times are getting worse. So we will need to investigate is how can we improve the performance of load times so that we don't win most and lose some. Right, and then analyzing the invalidation passes and what parts are used, duplicated. So analyzing what is actually duplicated across packages, developing tools for that, making developers' life easier. Right? That's once we have these base features and making sure that we've gotten the big wins out of the way, that we can look at across ecosystem wins.
All right, and with that, we are done. Again, I'm Tim Holy.
I'm Valentin Churavy.
And we thank you very much for listening and your attention. One of the things that we want to close with is just a thought of sort of what can you do to help ensure good precompilation in your package. So certainly looking into SnoopPrecompile when that gets released, which should perhaps be by the time you're watching this video. That is a useful thing to do. The other thing is that all of this precompilation work, as I mentioned, benefits from not having your code thrown away by invalidations. So if you've never taken a look at invalidations with respect to your package, any work you do on that from now and until later will set you up in a much better place to take advantage of all of this work. And with that, we are done, and we hope you enjoy the rest of JuliaCon.